Hello and welcome to my report of Destructive Testing Laboratory. We do the destructive testing to understand the mechanical properties of a material. This will be related to mechanical design. In order to choose the right material when we are designing an object, we have to know how a material will react if a certain force is given. For example, if you want to create a shelf, we have to build it from the right material. So when items are placed on it, the material that makes the shelf won't break.
There are two types of objectives in this experiment. The general objectives, which are to understand the elastic deformation and plastic deformation of a material, and processing data and analyzing it so we can know the strength of a material both in theory and practice. And specifically, we are doing this experiment to study about engineering stress strain calculations and actual stress strain, determine the yield strength, determine the elasticity modulus, determine the maximum strength, observing the necking phenomenon, and determine the level of metal resilience tested through calculating percentage of elongation and area reduction. These are the apparatus of this experiment. There are ASTM E8 specimen, the tensile machine, ruler and permanent marker, and vernier caliper. Before we start testing the material, we are measuring the dimension and the thickness to make sure it applies with the ASTM E8 standard of specimens. After measuring the dimension of the specimen, we weighed it on a weighing scale and it shows 123 grams. And after that, we put the specimen on the tensile machine. This tensile machine will pull the material with a certain forces, with a certain pulling rate. So obviously, it will create some necking and the fracture of the material. Then the pulling is started. The tensile machine will pull the material with the rate of 5 millimeters per minute. And then the time has come. The material shows necking already and it will fracture shortly. Bam! This is the material after being tested. You can see there is a little bit like cone shape on top of the material. This is the data that we got. We only got the elongation and load data, and then we calculate the strain and stress data. Now let me explain you how I get the strain and stress value and also the true strain and true stress value. For the strain value, I calculate the elongation value divided by the initial length of the specimen. For the stress, I calculate the load divided by the cross-sectional area of the specimen. And then for true strain, I calculate it by getting it to the natural logarithm ln of the strain data plus 1. And then for the true stress, I get it from multiplying the stress value times 1 plus the strain value. After we calculate the data, we can get some values of a certain things. The first one is UTS, which stands for ultimate tensile strength, which is the maximum stress that can be held by the material before the fracture. The value of the UTS can be determined by dividing the maximum force divided by the initial area, cross-sectional area, and the UTS value that we got is approximately 277 megapascal. The next one, BTS, or breaking tensile strength. Breaking strength is determined by dividing the load when the test material breaks, or F breaks, with the cross-sectional area of A0. So the equation is F break, the force when the material breaks, divided by the initial area, cross-sectional area. The BTS value that we got is approximately 170 megapascal. And then we can also calculate the elongation. Elongation is, in short, the increase of length. the elongation rate from our experiment is 36.55%. A metal is influenced by a force, so when the force is being removed, there are two conditions that will happen. When the specimen returns to its initial form, it's called a elastic deformation, and when it's not getting back to its initial shape, it's called plastic deformation. And after we calculate the data, we got the elasticity value is over 13 billion. Before we get to this stress strain graph, let me explain you what are the things that are included in this stress strain graph. There are Young's modulus, there's yield strength, the ultimate strength, and fracture. From the yield strength to ultimate strength, it's called the area of strain hardening, and from ultimate strength to fracture is an area called necking. And this is the engineering stress strain graph. You can see that the graph goes flat on the ultimate strength before going down until it fractures. And then there's a difference between engineering stress strain graph with the true stress strain graph, which is shown here. The true stress strain graph tends to climb higher and not getting flat, so the graph goes up, and then sometimes it will drop down and fractures. There's the fracture point over there. From the experiment that we have done, we can conclude that the material that we got is cast iron G4000 series.